Hi students, in this tutorial we are going to learn about torsion in Strength of Materials 2 subject. So this is the syllabus content for the torsion unit. It is the syllabus of JNTU Hyderabad. You can see it is divided into two parts: torsion of circular shaft and springs. So torsion of circular shafts and springs. Here you can see the detailed syllabus content. So basically, uh, what is meant by a torsion? The torsion is nothing but an action of twisting. Okay, action of twisting. You can see in the on this bar, uh, around the axis of the member. You can see here, this is the axis of the member. Around the axis of the member, there is some force is applying. Around the axis of the member, there is a force applying. That force will going to twist the member. Okay, that force is going to twist the member. You can see here the action of twisting, or the state of being twisted, especially one of the end of the object relative to the other. Okay, so means one of the end of the object, in the sense here you can see if it is fixed at one end and free at the other end, if you apply a twisting force here, eventually the resisting force will develop here. Okay, the resisting force which is opposite to this twisting, opposite to this twisting will develop at the fixed end. So here, the opposite resisting force will develop. The combination of these two forces will twist the material. Okay, the combination of these two materials will twist the material. Yeah. Here you can see this is the member. Okay, I'm applying a twisting force here. I'm applying a twisting force here. So the resistance force will develop here. The resistance force will develop here. Due to this resistance force, this member is going to twist. This member is going to twist. Okay. Due to this resistance force, this member is going to twist. Uh, Now we are going to see the derivation. Now we are going to see the derivation for this torsion. Okay. Here you can see A, B. This is the center of the member C, and this is D here. Okay, A, B, C, D. This is the circular member. So the circular cross section of this member looks like this. Okay, the cross section of the member will looks like this, and you can see here. So whenever I try to apply a twisting force here, okay, whenever I try to apply a twisting force here, this D will change due to the twisting in the material. Due to the twisting in the material, this D will change its position to D dash. Okay, this D will change its position to D dash. D will become D dash. Means it moves from this place to this place. Okay, it moves from this place to this place. We will assume this angle as phi. Okay, we will assume this angle as phi. You can see here also. So this as theta. Okay, so this is from D to D dash, and here it is O. So now you can see after applying the torsion, the member the member D is moved. The member D is moved from the point D is moved from here to here. So now, if you look into this shear strain, if you find out the shear strain for this member, shear strain. So we all know that change in length to the original length. So the strain is nothing but change in length to the original length. Here Shear strain in the sense distortion per unit length. Okay, distortion per unit length. Distortion is nothing but the change in length, the changed in length here. That is nothing but from d to d dash upon length. Okay, d to d dash upon L will give the shear strain. So that will be uh, we can write it as d to d dash by cd. From here you can see, from here we can write d2 d dash by cd, and also we can write, from this diagram, if you observe, if you give tan theta, if you apply a tan phi, if you apply a tan phi, you will get dd dash by cd. So now neglect the small angles, so that will be phi equals to dd dash by c. So now uh, this will be the phi value. Okay, this will be the phi value from this diagram. From this cross section we can find the length of this arc. Okay, from this cross section we can find the length of this arc. That will be d dash equals to arc. Okay, d dash equals to arc. That will be equals to r theta. Radius into angle will give the uh, radius into angle will give the length of the arc. Okay, so now we are going to substitute this d dash into the above equation. So that will give us phi equals to r theta by cd equals to l. So remember this, remember it as equation 1. Okay, remember it as equation 1. So then we all know that Young's modulus equals to stress by strain. In a similar way, shear modulus will be equals to shear stress by shear strain. Shear stress by shear strain. So this is our shear strain. Okay, this is our shear strain, and that will be equals to C equals to shear stress. We will normally denote with the tau. Okay, tau by c theta, sorry, tau by shear strain, this value r theta by n. Okay, r theta by n. So now we can write it as simply c theta by l equals to tau by r. Consider it as Roman number 1 equation. Okay, c theta by l, tau by r. We got half of the equation. Okay, we got the half of the equation, and then now we are going to derive another half of the equation. Okay, now we are going to derive another half of the equation. So to that I am going to write a diagram here. So this is the cross section. This is the cross section. So this is the cross section of that shaft. Okay, I am going to consider a small element or small element on the cross section. Okay, this is that small element. Okay, this is that small element. This is that small element. So now here I am going to find out the force on this member. Okay, the force acting on this ring. So the force acting on this ring, because normally the torsion is applying like this. Okay, the torsion is happening like this. You can observe here. The torsion is happening here like this. Okay, the torsion is happening like this, and now here I'm going to apply. I'm going to find out the force, whatever the force due to this torsion, what is the force happening on this small strip. So we all know that to find we all know that this will be the small portion. You can write it as dA, and this is dr. Okay, this is dA and dr. So now small amount of force acting on this ring will be df equals to tau into dA. I'll explain how this one is came. Okay, I'll explain this. See here. So normally stress, okay, stress equals to force upon area. Okay, this is the normal case. Here the stress will be a shear stress. Okay, the stress will be shear stress due to torsion. So for that case, shear stress tau equals to force upon area. So that will be we are finding out on a strip. So that will become df equals to tau into a. Here tau into dA equals to df. Tau into dA equals to df. So that is the thing we have written here. Okay, from this equation we can substitute tau value here. That will become df equals to c theta by L. This capital R will become smaller. Okay, smaller into dA. Okay, capital R smaller into dA. Okay, now we are going to see the torque. So basically we all know that movement equals to force into perpendicular distance. In a similar way, torque equals to force into the perpendicular radius here. Okay, the force into perpendicular radius. So here the on a small strip the torque will be dt and the force will be df and the radius will be small r. So dt, you can see we can substitute this df in dt. So dt will become c theta by l r dA into R again. So that will become R square. Dt equals to G theta by L R square dA. Okay. So this is the torsion equation for a small strip. Okay, for a small strip in a member. If you want for the total strip, if you want for the total member, we need to integrate this equation. So we, in that case, dt equals to, so this is the constant. So g theta and L will not going to change. Okay, for a member. So g theta L integration of R square dA. If you remember moment of inertia, if you remember moment of inertia formula, if you remember this R square dA, this R square dA will become uh, moment of inertia. Here we'll call it as polar moment of inertia. So that will become T equals to G theta by L into J. So the term J represents polar moment of inertia. The term J represents polar moment of inertia. So now T by J equals to G theta by L, or G or C. Uh, C theta by L, C theta by L, C theta by L. Here also C theta by L. So G or C or N. We can represent moment. We can represent polar moment of inertia with J, and shear modulus with C, N, and G. Okay, anything we can use. So now this will become equation 2. If you see, if you combine the equation 1 and 2 here, you will get T by J tau by R and C theta by L. T by J tau by R and C theta by L. This will be your equation. Okay, this will be your equation. C by L tau by R. You can see here C theta by L tau by R. So C theta by L also equals to T by J. So now we can write T by J tau by R C theta by L. So this is the torsion equation. So this is the torsion equation. Remember this. T means torque here. T means torque here. Tau means shear stress, and R means radius. J means polar moment of inertia. Polar moment of inertia, and L is length. We all know that L is length. Theta is angle. Okay, angle of twist, angle of twist, and C is shear modulus. Shear modulus. C is shear modulus.